Hi, my name is Reyne from the University of Sydney, and I'll be talking through sample problem W. As I've done previously, I will be going through the first three tests just to rule out options. So we can see from our unsaturation test that it is negative. There are no double or triple bonds. We can see from our oxidation test that there is nothing that can be oxidized. And from our carboxylic acid test, we can see that it is also negative and there is no carboxylic acid present. So that's handy. It rules out a bunch of options. Now, I'm going to skip past IR and mass spec. I like to go to the carbon and proton NMR first to get a bit of a feel for what the backbone of the structure is, and then I come back to these to try and confirm things. So if we scroll on down to carbon and proton NMR, we'll start with carbon, and I'll just label these arbitrarily. So we've got peak 1, 2, 3, and 4. So this is suggesting 4 carbons as a lowest ratio, remembering that this could mean that there are actually 8 or 12 carbons, but I tend to work in the lowest ratio first. And when I come back to the mass spec, that helps me to work out whether I need to increase the ratio. What I can also pull out from the carbon NMR is that peak 1 is very de-shielded, right on down towards 180 ppm. And that's normally what we see when we have, for instance, something like a carboxylic acid, an aldehyde, a ketone. Those are kind of examples. Now, we've already ruled out an aldehyde, which can be oxidized, and that test was negative. We ruled out a carboxylic acid, because that test was also negative. But a ketone is still an option. So that's something to bear in mind. We can see then that peaks 2, 3, and 4 are then down in the kind of alkyl region, but staggered, which to me suggests that they are potentially a chain away from whatever is causing that deshielding, and therefore the effect of that deshielding decreases as distance increases. Now, proton NMR is an interesting one, and I'll come to why it's interesting in a moment, but I'll first label it. So we've got 4 peaks. So we've got A, B, C, and D. And I might start with D and work my way backwards. So D, we can see the classic terminal CH3 kind of case where we have a peak area ratio of 3 protons present. And we also then see a multiplicity of 3. It's a triplet. Now, if we remember our n+1 rule, that tells us that there are 2 protons next to it. So we're always thinking CH3 and then a CH2. We then see our next peak at 1.64, peak C, has a peak area ratio of 2, so 2 protons, and it has a sextet, a multiplicity of 6 peaks. So by our n+1 rule, there must be 5 protons around it, and that would be the terminal 3 in the CH3, and it must also be a CH2 on the other side. And we can confirm that in a moment, but that's what it's suggesting. Peak B has a peak area ratio of 2, confirming that it's a CH2. If we go CH3, CH2, CH2, and it only has a triplet. Now, this is interesting because if it only has a triplet and we already know that there's a CH2 before it, that must mean that the next carbon along must have no protons present. So we need to keep that in mind. And here is the really strange thing. Peak A at a shift of 7, so something that is fairly de-shielded, only has a singlet, which we've tended to see for alcohols or for carboxylic acids, but it has a peak area ratio of 2. And this is odd, because even if we had 2 alcohols, the chances that they're on the same carbon is fairly unlikely. And we can kind of confirm that when we go to our mass spec and to our IR. But we need to think about, is there anything else that's kind of like an alcohol, but could have 2 protons on it? And the only thing that comes to mind for me is something like an amine. So an NH2, where you have 2 protons on there. Amines can participate in hydrogen bonding. They're not as good at it as an OH, but an NH2 here might fit the data that we're seeing. The quickest way for us to test this is to come back up to not our mass spec, but our IR. So we can confirm a couple of other things here. So for instance, we can see this classic peak CH stretch. We can see our CH bend. Interestingly, we can see a strong peak here, which to me suggests C double bond O, which lines up with our highly de-shielded carbon. Okay. But remember, there's no carboxylic acid. So this is just a carbon double bond oxygen so far as we know. And then we see this kind of weird shape. Now, in some other examples, you may have already seen me talk about OHs having very broad peaks, but this isn't necessarily that broad. It doesn't really look like the same thing. And in fact, it's kind of like two peaks, or you may see it described, if you look it up online, as a double dagger style peak. This, at this particular sort of range, at about 3,300 to 3,500, is indicative of an amine, or of a carbon to nitrogen, okay? And that's really important to note, because that kind of confirms, or at least gives us more evidence towards the idea that this peak in the proton NMR, so peak A, is potentially the amine, the two protons on that amine. The way that we can confirm this beyond a doubt is then, of course, to come to our mass spec. So we've come up with a hypothesis. We think that there is a carbon-oxygen double bond. We think that there is an amine present as well. And then we know, if we just assume that the lowest ratio is correct, we have a number of carbons and a number of protons around. And we can see this molecular ion peak quite small towards the end. We're looking for 87. So let's add up all of these things. So from our carbon, we have 4 carbons, which would equal 48. We're saying that there is 1 nitrogen, which would equal 14. We're saying that there is 1 oxygen, which would equal 16. Now, bear in mind, this is me doing a trial and error approach. I'm just saying, let's assume this, give it a go, and if it doesn't work, we need to reevaluate and come back with something else. And the last thing is then the number of protons. If we add these up, we can see we have 9. So 3 plus 2 plus 2 plus 2. So we end up with 9 hydrogens, which will equate to 9. And if we sum all of these together, we will have 30, 78, 87 on the dot, which is great. This adds up with what we've already kind of worked out in terms of the other data available. So the last thing we need to do then is work out, well, what does the structure look like? We know that there's a carbonyl. We know that there's an NH2. We know that there are some carbons present. And I think this is where the positioning or the shifts of these carbons comes in handy, as well as also what we see in the proton NMR. We'd already established that there must be a terminal CH3 to a CH2 to another CH2 to a carbon that has no proton on it, hence why we see that triplet for peak B. And that would then suggest that this is probably where our carbonyl is, as well as our amine. Now, depending on how much you've done in terms of organic functional groups, if you have a carbonyl next to an NH2, we actually call this an amide. So it is its own kind of functional group. So when we come to name this, or in fact, before I name this, I'll quickly add in the labels. So we can say that this is carbon 4, carbon 3, 2, and then that's carbon 1, the very highly de-shielded carbon. And then for proton environments, if we go to blue, we would expect this to be D, C, B, and then A is actually those protons in the nitrogen, as we've talked about. So to name this, we would then name this, we have a carbon chain of 4, which is bute. And then because it's an amide, we would actually say this is butanamide. And we don't need to specify where the amide is, because if it was on another location, it wouldn't work. So butanamide would be fine. But if you wrote butan 1 amide, I would also accept that. All right, that will wrap that one up. Thank you.